Hi and welcome back. This podcast should be a little bit shorter because we're not, taking notes. We're just doing homework problems together. So the last podcast was on limits involving infinity. We were looking at vertical and horizontal asymptotes. Now I've selected problems 5, 17, 19, 23, 29, and 41 to do with you. I'm using the Thomas's Calculus book here, and I'll be using this interactive feature so I can pull up the problems, make them bigger for you to see. All right, here comes number 5. Now, before I read this problem to you, in fine print, I want to read the directions of the author. It says, find the limit of each function as x approaches infinity and negative infinity, but it says you may wish to visualize your answer with a graphing calculator or computer. So that's what I was saying earlier, we often like to type these things in the calculator and take a look. Okay? Okay, so I wrote it bigger so you could see it. Let's just start off with the limit as x approaches infinity, okay, for this function. You're probably tempted to put it in the calculator. I'm going to take an algebraic approach. We said divide by the highest power of the variable in the denominator. Well, 1 over x, though, really means x to the negative 1. So the denominator, the overall denominator of this fraction, we're seeing the variable x to the negative 1. So if I divide 17, over x to the negative 1, and then 18 over x to the negative 1, and then plus, in essence, x to the negative 1 over x to the negative 1, if I take a look at that, limit as x approaches infinity of that expression, well, let's keep cleaning. Then the top will become 17x, okay? Down bottom, we'll have 18x, and then this expression right here will just be 1, okay? So it's like I'm manipulating this thing algebraically. Now, you may remember from the notes segment that we said now, when the degree of the top is the same as the degree of the bottom, you end up taking the ratio of the leading coefficients, ends up being where your horizontal asymptote is. So if you're just comfortable knowing that in your own mind, you might be thinking 17/18ths, because that's where the horizontal asymptote occurs. There's other additional steps we could write there, but we've shown that in previous podcasts. So let's take a look. 17/18ths. Oops, didn't let me type in there. 17/18ths. And it says fantastic. Okay. Now, that expression that I ended up with, if I would have stored an infinitely large negative number in there, and actually I went back to that expression, so where we left off basically was we had manipulated this into the form of 17x over 18x plus 1. If I took that additional step where I'm then again dividing by the highest power in the denominator, then I'd have 17x over x, all over 18x over x plus 1 over x. And, if I take the limit as x approaches negative infinity of that, let's see, this cancels, I'm going to have 17 over 18 plus 1 over an infinitely large negative number, in essence. So if you take negative infinity, basically, and store it right there, what happens as x becomes larger and larger and larger, even in the negative direction, this goes towards 0, right? So I'm still arriving at 17 over 18. Now that, I always try it analytically like that and with the algebra, and then take a look on the calculator just to verify. So I do want to mention that. So you would go to y equals, I don't know that I'm going to do all these on the calculator, but so you would have 17 over paren, and then I would type that denominator in as 18 plus x to the negative 1. So x up caret -1. Always try zoom 6. And like I said, you could use that trace feature. Trace, head on out. As x is becoming larger and larger and larger, what's happening to those y values? They look like they're capping off at like a 0.938. Now, what you could do then, 0.939, what you could do then is like verify is what's 17 over 18. So I'm going to hit second quit. 17 over 18. This is 0.94, yeah. So, you know, the problem is if you do use the graphing calculator, it's going to throw that decimal at you, you know. So you'd almost have to use algebra to get that perfect fraction. Okay? Let's try the next one. The next one is number 17. So you can see I'm on this chunk of problems, but I'm going to use this interactive button here that lets me do problems that are just like this, but perhaps different numbers. See? 17. All right, let's take a look. It says find the limit of the rational function, you know, as x approaches infinity and negative infinity respectively. For time's sake, I'm just going to play with as x approaches positive infinity. Okay. Now here on this one, we luck out once again. I'm going to write it bigger here. H of x equals 10x cubed over 14x cubed plus 4x squared plus 12x. And, you know, the limit as x approaches infinity of h of x is basically, if you divide by the highest power, which is in the denominator, which is x cubed, of every term, and, well, by now I'm basically going to assume that you're comfortable with that, you've done that. You know that basically you're going to be left with the ratio of the leading coefficients, 10 over 14. As your horizontal asymptote. So if that's your horizontal asymptote, then sure, as x gets bigger and bigger and bigger, those y values are going to approach that. Now we want to reduce that. You know, 2 into 10 goes 5, 2 into 14 goes 7. Survey says 5/7. Let's give it a shot. Okay, it liked that. In the negative direction, again, you know, if I divide every little thing by the highest power in the denominator and let x become infinitely large in the negative direction, I'm still going to end up with 5/7. And I'll let you explore that on your own, okay? But again, graphically, you know what, that's actually a really good one to explore graphically. I always say don't just believe me, you know what I mean? Never just believe me. Just type it in. Take a look. So 10x cubed divided by, and then we'll do paren. Here, I'll hit pause as I type it. Okay, so I've got it typed in. I'm going to hit zoom 6 again, like I always do. That's standard window. Okay, and you're noticing there might be some odd behavior there at origin, but we're not interested in origin in this problem. We're interested in, you know, as x tends towards infinity or negative infinity. Well, let's trace out. As my x's become larger and larger and larger in the negative direction, it appears as though my y values are capping off at about and I'm looking at that, you know, it's like 0.73. Even if I go way out, well, it went below 0.73. And sometimes you say, well, how low is it going to go? Well, that's what, again, that's where you can use that table feature. Let me delete what's in there. That's where you can say, gee, when x is negative 1500, you know, what's y? It's saying 0.714. And then, interestingly enough, second quit, if you look at 5 over 7, what we got? 0.714. See, so what we got here analytically, and then looking at the graphing calculator, matches. Okay? Let's take a look at the next one, which is number 19. Now this one I'm going to write out so you can see it. It's probably awfully small there. We're looking at the limit as x approaches infinity, and then it's eventually going to ask us negative infinity, but I'm just going to look at infinity for now. The limit as x approaches infinity of f of x. That's what it's asking us. And f of x is equal to 2x to the 8th plus 5x to the 7th. I'm just writing it bigger so you can see it. Plus 3 all over 7x to the 9th. Well, big note to self, the power in the denominator is higher than the power of the numerator. So hopefully you're thinking, gee, the horizontal asymptote is 0 when that happens. But we'll go through the math. So the limit then, if you divide everybody in the numerator by the highest power in the denominator and take a look what happens. So plus 3 over x to the 9th. In the bottom, I'm going to have 7x to the 9th, over x to the 9th. If I take a look at that, so I'm dividing everything by the highest power in the denominator. Clean that up. Let me grab another color here. Okay, x to the 8th and x to the 9th, there's going to be 1x left on bottom. Here there's going to be x squared left on bottom. Here there's just going to be a 7 left in the total denominator of the fraction. So if I clean that up, I'm arriving at 2 over x plus 5 over x squared plus 3 over x to the 9th all over 7. But the thing is, the limit, I'm just going to write over top of that, as x approaches infinity, well, if I put a large number in there, that's going to go to 0. Large number in there, that's going to go to 0. Large number in there, that's going to go to 0. So I'm basically ending up with 0 over 7, which is 0. Okay? So, and that's what we were saying. We were saying when the the power in the denominator dominates like that, horizontal asymptote 0 at y equals 0. So we'll put here 0. Okay. And like I said, same thing would happen in the negative direction. And I'm going to leave that one up to you to put in your calculator and take a look. But you can certainly verify that. Okay, and the next one on the list, I believe, is 29. I lied, 23. So that's the next chunk of problems down here. And you know how math books go. When they get higher numbers, sometimes it gets more difficult. 23 is the next one. Now we have some limit laws here. We have the the cubed root of a function, so it's perfectly legal for us to do this basically. I'm going to write it out. We're looking at the limit as x approaches infinity of the cube root of 1 plus 8x squared over x squared plus 1. Now your author even reminds you that it's perfectly legal then, to do the cube root of the limit as x approaches infinity of that, that rational function. So basically it's like do the inside first and then eventually cube root it. Okay? Well, I'm just going to talk you through this sort of analytically without doing too much fancy algebra. If you look at this rational expression in here, lead coefficient on that is 8, lead coefficient on that is 1, degree of the top is the same as the degree of the bottom, ratio of lead coefficients is 8 to 1, 8 over 1. So we're thinking that the HA, the horizontal asymptote, is basically at y equals 8. The ratio of the lead coefficients is 8. So that's good then, because then you're going to take the cube root of 8, which is 2. So we believe that this is going to be 2. Let's take a look. Yay. And again, I dodged the graph and calculator on that, but you certainly could do that. Now we're ready for 29. Now you know why I picked this, because there's fractions involved. Gotta love that. I'll rewrite it for starters. It's the limit as x approaches negative infinity, and then I'm going to write it in fraction form, because the cube root of x really means x to the 1/3, right? So you have x to the 1/3 minus x to the 1/7 over x to the 1/3 plus x to the 1/7. And there's lots of styles of thinking about this one, but the highest power in the denominator is 1/3, right? So 1/3 is a larger number than 1/7. But you're also noticing that they have the same power, like they have the same degree. The degree of the top is the same as the degree of the bottom. So again, we're inclined to take the ratio of the leading coefficients, which is 1. So the horizontal asymptote we believe occurs at 1. Now I could, like I said, go through the algebra on that, divide every little guy by x to the 1/3, but again, like I said, x to the 1/3 is higher powered than x to the 1/7, so it's going to dominate. And I'll just do that here. This is going to be 1. This is obviously going to be 1. This as the limit as x tends towards negative infinity. Well, as this grows, this dominates, it grows faster, than x to the 1/7. So this is going to go to 0. And same thing here, x to the 1/7 divided by x to the 1/3. I always think about the growth. The growth on x to the 1/3 is going to dominate, so that's going to go to 0. So we're ending up with 1. Let's put 1 in there, see how it likes it. All right. And again, you could certainly graph that as well. You could even type it in as, like I did, like x to the 1/3 minus x to the 1/7. You could type it in like that to take a look and trace as x approaches negative infinity. So you have lots of tools at your fingertips. You don't have to go the algebra way. You can go the graphing way. And then, let's see, we got 29, and the last one is 41. I actually really like this one because you have so many different ways that you could approach this. It's the limit as x approaches -9, and then it has that little plus sign. So remember, that means the limit as x approaches -9 from the right of this function, -4x over x plus 9. Well, basically, as I'm coming in towards -9 from the right, I'm looking at -8.8, -8.9, -8.9999, getting closer and closer to -9 from the right. Well, storing in those numbers into this expression is one way of doing it. You could store in numbers awfully close to -9 from the right and see what that's converging to. Might be just as easy to graph it. So let's take a look. So I like, when I'm doing left-hand and right-hand limits such as this, I really like to graph it and take a look. Because you do know there's a vertical asymptote at -9, but how do you know whether it plummets or increases quickly near that vertical asymptote? So, one of the fastest and easiest ways is to just take a look on here. So -4x over x plus 9. And then let's graph. Well, we'll do zoom 6 to be safe, because I don't remember what I had it on before. Aha. So now, see, as I'm coming in, now we can see it. I'm going to draw over top of the calculator. As I'm coming in towards -9 from the right, what's happening to this is shooting upwards, right, to positive infinity. And you could even, what you could do is you could even mess with the window to see what's going on the other side, like I would. I'd make your x-min, like, say, negative 25. Take a look. See that? See, as I'm coming in towards negative 9 from the left, my limit is negative infinity, but I'm coming in towards negative 9 from the right, my limit is positive infinity. So we want to put infinity here. You have an infinity tab here. See? So I really just wanted to say it's perfectly fine to use your calculator. You don't have to store numbers in and see what it converges to. It's fine to take a look. All right, good luck, everyone.